For pretty much our entire lives, we've lived by this simple, unspoken promise. Computers just keep getting faster, smaller, and cheaper. It's a given. But that promise, it's running smack into a wall. A wall made of pure, raw heat. So let's dive into the story of why this is happening and the incredible race to invent what comes next.
And yeah, I'm not being dramatic here. The very engine that powers our digital world is, quite literally, overheating. All that amazing, relentless progress that we've just come to expect is facing a fundamental physical limit.
Think about it. The device you're watching this on right now, it's powered by billions, literally billions of these things called transistors. They're just microscopic switches, flipping on and off at an unimaginable speed. Your phone, your car, the entire internet, it's all built on mountains of these impossibly tiny switches.
So what's the secret sauce inside each of these little switches? Well, it's something called a p-n junction. It's basically where two slightly different types of silicon meet up, and in doing so, they create a one-way street for electricity. This simple little gate is what allows a transistor to be either on or off. And that right there, that's what gives us our ones and zeros, the fundamental language of all computing.
For decades, the game was simple. The rule was just make them smaller. And boy, did we get good at it. Like unbelievably good.
Okay, just look at this thing. Seriously, this isn't some artist's concept from a sci-fi movie. That's a real, modern transistor. We've moved way beyond microscopic. We're engineering things with layers that are just a handful of atoms thick. The complexity is it's mind-boggling.
And this whole incredible shrinking act? Well, it has a name you've probably heard, Moore's Law. For 50 years, it's been the steady heartbeat of the tech world, the reliable clockwork that just kept giving us exponentially more powerful computers year after year after year.
But there's always a but, right? As we've pushed deeper and deeper into the nanoscale, that steady heartbeat, well, it's starting to get a little shaky. We've slammed right into a wall made of physics.
Let's try to put this in perspective. A modern computer chip can pump out over 100 watts of heat in a space just 1 centimeter square. To give you an idea, that's hotter than an electric stovetop packed into an area the size of your fingernail. It's insane.
And now let's zoom in, way down to a single transistor. Every time an electron zips through it, it's like there's a tiny bit of friction. It sheds some energy, and that energy becomes heat. This is called joule heating. And you have to remember, this is happening in billions of transistors, billions of times, every single second.
So we're getting hit from all sides here. First, these new, complicated 3D shapes we're building, they're actually terrible at letting heat escape. Second, a lot of the fancy new materials we're trying out, they're just not as good at conducting heat as good old silicon. And then there's this really weird part. At this tiny, tiny scale, heat doesn't even behave normally anymore. It doesn't just spread out. It shoots through in these waves, which are almost impossible to control.
So what do you do? I mean, this is literally the billion-dollar question for the entire industry. If we can't just keep climbing over this thermal wall because it's getting too hot, what's next? Is there another way?
Well, it turns out there might be a really clever idea that doesn't try to muscle through the problem, but instead just sidesteps it. And to do it, we have to dip into the incredibly strange world of quantum mechanics.
Instead of trying to climb over the wall, the idea is simple. We go through it. That's it. That's the idea that could change everything.
So say hello to our potential hero, the tunnel field effect transistor, or TFET for short. The key difference is huge. Instead of boiling electrons with energy to force them over a barrier, the TFET uses this wild quantum trick called band-to-band tunneling to flip its switch.
And the difference is just night and day. Look here, a regular transistor on the left, think of it like a dam. You have to pump in a ton of energy, which creates heat, to get the electrons to slosh over the top. But the TFET on the right, that's different. It's like applying a voltage makes the dam wall so thin that the electrons just sort of poof. They disappear from one side and reappear on the other. They literally tunnel through the barrier.
And that's the whole magic trick right there. Because you're not using brute force heat, TFETs can switch on super sharply, with way less voltage. This idea of a subthermal swing, I mean, that's the holy grail for engineers. It's the key to getting the same performance with a fraction of the power, which means a fraction of the heat.
Okay, so the theory sounds amazing, right? A total game changer. But actually building one of these quantum switches? Yeah, that's a whole other story. It takes some serious next-level engineering. It's like baking a very, very precise quantum cake. You need the right ingredients, right? You need special materials with just the right properties, things like group 3V compounds.
Then you have to join two different materials together with atomic precision. That's called a heterojunction. And finally, you have to shape it just right, often vertically, to get the most control possible.
And you can see how much this stuff matters right here. Look at the numbers. If you just make a TFET out of plain old silicon, your swing is way up at 116. Not great. Just by using two different materials, that heterojunction, it drops to 95. Better. But then, when you use the right material, like indium arsenide, damn, you get down to 61.2. That is incredibly close to that perfect 60 number everyone is chasing. So yeah, the materials are absolutely crucial.
And it's not just the materials. The actual shape of the thing matters a ton, too. We used to make transistors that were totally flat. Now we build them up in these 3D shapes, kind of like fins, so we can get more control. That same evolution in shape is just as important for making these new TFETs work.
So really, it boils down to a three-step process for the engineers. Step 1. Pick your materials. And exotic stuff usually beats silicon. Step 2. Figure out the structure. And a heterojunction is pretty much always the way to go. And step 3, optimize the geometry. Build it up instead of out. Every single one of those choices makes a huge difference in how well the final switch performs.
Look, I know this is super complex stuff, deep in the weeds of material science, but what it all points to is a potential future. A future where our computers can keep getting better without just melting.
And this is where it gets really cool and very 21st century. I mean, trying to find the perfect recipe by hand would take forever. So what are researchers doing? They're using machine learning to simulate and test thousands of different materials and designs, way faster than any human could. It's like we're using our current computers to invent the next generation of computers.
So that's where we are. We're at a real crossroads. The old road, the one we've been on for 50 years, is basically on fire. The big question now is, can we perfect this strange quantum leap through the barrier and build the next generation of technology on a foundation that's not just faster, but fundamentally cooler? The race is on.